Welcome, ladies and gentlemen, to 22.2, which is entitled Ohm's Law. And Ohm's Law is the most important equation in all of electronics. Anywhere you go, you're going to run into Ohm's Law. And so what I have here, I have a video that's explaining Ohm's Law. And we're also going to talk about schematics today. How do you read a schematic? What are some simple symbols that they use inside of schematics? How do we read something schematically? So let's get started.
A lot of people are turned off from designing circuits because it can require a bit of math. And while many engineering equations could easily turn off newcomers, probably the most useful one is thankfully quite simple. It looks a little bit, in fact, it looks exactly like this. And it's called Ohm's Law.
This magazine is one of my favorite magazines to look at. The library has it. It's a magazine totally dedicated to people who make things. It's really cool. You should check it out.
Ohm's law defines an important relationship between three very important electrical properties: voltage, current, and resistance. And just in case you're wondering, current uses an I instead of a C because C is used for coulombs, which are a unit of electrical charge. But we won't get into that right now. Anyway. You've likely heard the terms used before, but just to get things straight, let's go over what they are. Voltage is defined as a difference in electrical potential. You can imagine it kind of like this. If we have 2 points at different heights, water at one point and water at another point, if we connected those two with a pipe, water would flow from the higher point to the lower. This difference in height between points A and points B is kind of like a voltage. So, when we talk about a 9-volt power supply, we're really talking about 9 volts difference between the supply's positive and negative terminals. And of course, voltage is measured in volts. Make sense? Current refers to the rate at which electrons flow through a given point. And current is measured in amperes. And finally, resistance measures an object's opposition to the flow of electricity. It's a bit like a narrowing in our pipe that would cause a change in current. So, like I said before, Ohm's law defines how those three properties relate to one another. Now, to remember this relationship, we can use this pyramid diagram. To find voltage, we multiply current by resistance. To find current, we divide voltage by resistance. And likewise, to find resistance, we divide voltage by current. As long as we know 2 of the 3 values, we can rearrange this equation to find the third value. Thanks to algebra. Let's say I have a 9-volt battery, which I do. So voltage is 9 volts. I want to limit the current in my circuit to 30 milliamps. And that would be 0.03 amps. I need to figure out what value resistor to use to limit the current to that amount. Ohm's law tells us that resistance equals voltage divided by current. The resistance is equal to 9 divided by 0.03. Therefore, resistance equals 300 ohms. So a 300 ohm resistor. Equipped with Ohm's law, there's nothing you can't handle. Alright, there'll be a few things, especially outside of like circuitry. It's helpful, definitely, to have around. Use it.
So Ohm's law, it's my favorite. Very useful equation. It just simply states that voltage equals current times resistance. And we kind of went through some conceptual questions that sort of dealt like this. Right here, when we looked at this question yesterday, we talked about which one has a higher voltage. Now, these both have the same voltage. They both have the same electrical potential, meaning that they're at the same height. So there's the same amount of gravitational, force pulling down on both of these. So there's the same amount of pressure. But the amount of current that flows through the system is dictated solely by how thick the pipe is. So if I have a larger pipe that has less resistance, more current is going to flow if I've got a pipe over here that has a tighter, less current. So more resistance over here, and they're inversely related. You've got more resistance, less current. Less resistance, more current. Over here, less resistance, bigger pipe, more current. More resistance, smaller pipe, less current. Simple as that. And he had touched on the units for resistance, which is ohms. There's a few factors that affect the resistance of something. The longer something is, the more resistance it has. Resistance increases as cross-sectional area decreases. So if you have a thicker cable, people that do car stereos know this, that you have to have really thick cables when you're running into your amps because they pull a lot of current. So the more current that you want, the bigger the cable. Temperature, the cooler something is, the more current it can carry. So this is like supercooling. We did this when we had liquid nitrogen. We showed that it was superconducting when it got cold. And then finally, different materials. There are certain materials that are better at conducting than others. It turns out that silver and gold are actually really good conductors. The next thing I want to talk about is schematics. These are some common symbols that we use in schematics. Like if we have a conductor, we just draw a line. A switch is this, it opens and closes. Closes meaning that it makes the electrical connection. A fuse is this little S here. A capacitor we'll get to. A capacitor is a place to store charge. It's like a water tank, if you will. Resistors are those kinks in the hoses. So you can actually visualize it as like a kink if you were to kink the hose. And this is a variable resistor, sometimes referred to as a potentiometer. An inductor is a coil of wire. Remember we took coils of wire and we made magnetic fields? That's called an inductor. If you have an electrical connection, a lot of times you fill it in with a dot. And if there's no electrical connection, sometimes you'll see it jump over top of. the ground. Here, this is a lamp. There's a whole bunch. There's literally a slew of different types of schematics. I went on SparkFun's website just to pull up a bunch to show you. Here's resistors, 1,000 ohms, 1 kilo ohm, variable resistors, capacitors, inductors, SPST, single pole, single throw. That's what that stands for. Single pole, dual throw, dual pole, dual throw, all sorts of stuff. If you've got a source, like a voltage source, like a battery, that's going to be a direct current. Batteries are direct current. Plug something into the wall, you get what's called alternating current. So this is an alternating current source. This is a direct current source. Here, if you've got a battery, this is one cell, and if you've got 2 cells, and if you had 3, you just keep piling them on. The long side typically represents the positive. We aren't going to use like a third of these things, but it's just kind of fun to see. These are diodes, so like this is a light emitting diode. See how the lines are going away, and if the lines are going towards it, that's a photodiode. It senses how much light's in the room. These are transistors right here, NPN or PNPs, kind of neat. These are logic gates, so integrated circuits, op amps. These are crystals and resonators, headers. These are transformers right here, relays, speakers. I mean, it just goes on and on and on. And if you can go online and you can type in schematics, and you can get really simple schematics. You know, like, oh, I know right now that this is a diode. Here's a resistor. Here's a battery. This looks like a transistor. Here's a capacitor labeled C2. Or you can get really complicated ones. Let's go back here. Oh yeah. This looks like it's got lots of components. I think I clicked on this one already, yeah. This looks like an IWA. This looks like some sort of amplifier, like stereo right here. They get really complicated. Here's a simple circuit that your book has in it. It's got a 12-volt battery hooked up to a switch, and the switch goes to a motor, and then the motor comes down here to a potentiometer, and then back to the battery. So basically what this does, you can switch it on and then make the motor spin faster or slower, depending upon where you have the potentiometer at. So here's the schematic symbol for this. Here's your battery, and it goes to the switch. The currents are going this way, and here's the schematic for a motor, and the potentiometer, and then back to the battery. This is the one example problem that I'm going to do for you guys today. It's example problem 2. It says current through a resistor, and it's got a simple drawing here. It says a 30-volt battery is connected to a 10-ohm resistor. What's the current through the circuit? So what I'm going to do, I'm just going to quickly draw what's going on here. Here's my battery, my positive side, here's my negative side, and it looks like there's an ammeter. So I'll designate that with the letter A. And then there's a resistor. And my current is going to actually travel in this direction. Current always travels from positive to negative, conventionally. And so we're going to use Ohm's law, V equals IR, to figure this out. So we've got a 30-volt battery. What current? And the resistance is 10 ohms. So this is pretty basic, coming at you. 30 divided by 10 is 3. So we're talking 3 amps of current are traveling through the veins of this. So this meter right here is going to read 3.00 amps. So Ohm's law, pretty important.